Therefore, it is my pleasure to introduce Amrit from Zilliqa. So guys, a huge round of applause for Amrit from the project Zilliqa, who will talk about blockchain scaling technology. So, very welcome, Amrit.
Thank you.
Here we go.
Okay, very good afternoon to all of you. I'm Amrit. I'm essentially a researcher at Zilliqa, where we're trying to build a scalable blockchain platform. Now, before we actually jump into the details of the talk, let me ask you a very simple question, which is, how many of you have actually used a blockchain application before? Okay, quite a few, quite a few. So if you have used such an application, even in terms of payment, like Bitcoin, you must have heard of this application called CryptoKitties. So it's a very, for those who don't know, it's a very simple application, a game which is based on Ethereum, where you can buy and sell digital tokens. And then you can breed them, and then you can have new kittens, and that you can sell them again. Now, don't ask me why and since when cats have started laying eggs. But, in this world of crypto kittens, you can do anything that you want. So now, CryptoKitties became very popular in, let's say, December last year, to an extent where a simple and cute cat, this one, was sold for over $100,000 worth of Ether. So you can assume how popular this application was. And this application was so popular that it actually affected the underlying blockchain platform. So if you can see, when it was launched, you see that there's a huge spike in the gas fee. So when people started using this platform, they had to, they were limited by the underlying throughput of Ethereum blockchain, and they had to pay a really huge gas fee to actually start playing and exchange tokens there. So this clearly shows that if your underlying blockchain platform is not very scalable, then you will end up with these issues. Now consider yourself as a blockchain developer or an app developer who wants to build a very popular gaming application, for instance. And the moment it becomes very popular, you don't know what to do, because the underlying blockchain platform is not able to give you the support that you actually want from it. So what do you do in those cases? The simple and the very obvious solution is that you kind of increase the barrier of entry. So you would say that if you want to play this application, play this game, then you have to put a larger fee. So this is what exactly the CryptoKitties developers they did. So they doubled the price of breeding cats on the blockchain application. Of course, it does reduce traffic to some extent. But again, as a blockchain developer, you do not want your popularity to become a threat for yourself. So what you want to do here is to ensure that the underlying blockchain platform on which you are actually building this application gives you enough support, so that even when your application becomes very popular, you would actually be able to support that many users and that much of traffic. So putting things into perspective, so here's what popular blockchain platforms actually perform in terms of throughput. So blockchains like Bitcoin and Ethereum are they process around 5 to 10 transactions per second on average. And if you compare it with a very real-world application, which is payment, a very simple one, like Visa, they process around 5,000 to 8,000 transactions per second on average. In peak hours or during Christmas time, that can actually go even higher. So you can clearly see that there's a huge gap between what popular blockchain platforms actually deliver and what you actually need when you deploy a real-world system in this current setting. So there's a clear problem. So there's this underlying scalability problem that every blockchain that exists today, at least the popular ones, they face. Now everyone knows this, and as a result, you have all kinds of solutions to improve or to solve this problem. So let us go with the first very simple solution, which is increasing the block size. So for those who are familiar with how blockchains and Bitcoin, for instance, work, so you have blockchain is a chain of blocks, and each block has a bunch of transactions. So if you increase if you increase the size of your block, then you actually can fit more transactions into it, and hence you can process more transactions per second. In very layman's terminology, you can consider it to be a bus which has a capacity of, let's say, 40 passengers or 20 passengers in a bus. And if you increase the size of the bus, which means that you transform your regular bus into a double-decker bus, you'd be able to double the capacity of your bus. So you'll be able to handle double the load. But again, it's only limited, right? You cannot go beyond a double-decker bus, because if you do that, you will end up with such a case where if you are fear of, let's say, heights, you won't want to take a ride on this bus. And even for security reasons, certain countries or even certain cities, they have a maximum height, so these buses can't actually go through it. In more technical terms, scaling your block size does give you high throughput and gives you very immediate result, but it's very limited to a certain extent. You can go from, let's say, a block size of 1 megabyte to, let's say, 2 megabytes, but you cannot increase it from, let's say, 1 megabyte to 10 gigabyte. It's not going to work because of network limitations, because you have to transport that block to every node in the network. And that's not very scalable in that sense. So what are other solutions? There's another line of solutions called off-chain solutions, where what you try to do is you want to reduce the traffic that actually goes to the main network, the main chain. So for instance, what you do is, let's say you have a very fancy electric car, and you take your car to this charging station every morning, and you charge your car, and then you pay a small amount of money as a return. Now, what you do instead, in this case, that you don't want to pay this charging station every single morning. What you do is you kind of write a contract with this charging station. You would say, you know what, I'm going to pay you, I'm going to aggregate certain payments, and I'm going to pay you in, let's say, after a month to some extent. And after that, you have set up your contract. You would send offline transactions to your charging station, and the charging station will collect all those transactions. And at the end, it will submit just one transaction and claim all the amount that's due. So what you're trying to do is you're trying to move traffic from the main network and make it off-chain. And so you can have a very high throughput. But again, it has its own set of issues, which is essentially, you lose certain properties of the blockchain. You also sometimes have to maintain an overlay network on top of the main network. And it has its own set of issues. There are other solutions, for instance, delegated consensus protocols, where what you try to do is you actually change the entire consensus mechanism that you have on the network. For instance, what you could do is, instead of asking, so if you know how Bitcoin works, what happens is when you send a transaction, every full node or every node in the network processes your transaction and validates it. Now, instead of doing that, what you could do is, you could say, I'm going to select a small group of people, and those group of people are only the ones who are going to process and validate my transactions. So because you're shrinking the network, you can actually have very high throughput. But again, there are certain assumptions that come into play. For instance, what's the size of that delegate? How many nodes should you have in there? What kind of trust you maintain? Is it semi-trust, or do you maintain, or do you have some trust on those delegates? So it's essentially like, in layman terms, it's essentially like a parliament where the entire country doesn't make decisions on policies. You elect a parliament, and the parliament makes decision. So it has its own set of issues. So I gave, 3 general solutions to scale blockchains. The one is increasing the block size, then off-chain, and some other consensus protocols that exist today in the literature. What we are trying to do is to build another scalable blockchain platform called Zilliqa. And the idea that we use in Zilliqa is called sharding. So what exactly it is? So before I talk about it, let me tell you that sharding is pretty known. If you're familiar with databases, sharding is, it comes from that domain, the database domain, where the idea is when you have, let's say, large matrix, what you could do is you could divide that table or matrix into certain rows, and one server would only manage load that comes to, let's say, first 2 rows or second 2 rows, or so on and so forth. But it was not known whether you could apply this idea in the context of blockchain. So some of our team members wrote a paper, an academic paper, to show that you could actually employ sharding even in the blockchain space, and you could use that idea to actually scale the blockchain infrastructure. So this is a high-level introduction of how sharding works. So as I said a minute ago, in Bitcoin or in general blockchain network, when a user sends a transaction, every single node in the network processes your transaction. It gives very high security, but it's also very redundant to some extent, because you don't want a single transaction to be processed by every single node of, let's say, a network of 20,000 or 30,000 nodes. So what you could do instead is that you could take your large network of, let's say, 10,000 nodes, and you could divide them into smaller groups, let's say 1,000 nodes each, and then you can have 10 groups. In a way that you could have one group processing completely different transactions compared to the second group, and so you can have, you can process non-conflicting transactions in parallel. So in a way that if you have more smaller groups, you could have more throughput, and it essentially gives you linear scalability. So the more throughput you will get, the moment you have, the moment your network expands. So this is something which is pretty counterintuitive, because if you compare with, let's say, Bitcoin or Ethereum blockchain right now, or any existing proof-of-work-based blockchain that you have right now, I mean, if you add a node in the network, you have to transport that you're kind of, the throughput actually goes down to some extent. But here it should increase. And this is the idea of sharding, essentially. So you divide, and then you conquer. So, so what we did was we implemented this idea, this theoretical idea, into a real-world application, into a real-world system, and this is what Zilliqa is. So we actually observed that if you have a network of, let's say, 1,800 nodes, you would observe a throughput of around, we observed a throughput of around 1,200 transactions per second. And if you double your network size from 1,800 to 3,600 nodes, you actually double your throughput as well. From 1,200 to around 2,400 transactions per second. So these are real numbers that we observed from our internal testnet. Well, so if you put things into perspective, Bitcoin and Ethereum, they process around 5 to 10 transactions per second, and Zilliqa, with a network size of 3,600 nodes, can process around 2,500 transactions per second. Don't forget that it gives you linear scalability. So if you have more nodes, you can have a better throughput, much beyond 2,500 transactions. So in general, what we try to do is to build a new blockchain platform, and that will be scalable. And once you have a very scalable blockchain platform, you won't have issues the way CryptoKitties had in terms of, let's say, transaction fee, gas fee, in terms of what happens when my blockchain application becomes very popular. Do I have to worry about the user base? Do I have to reduce in some way the user base that interacts with my application? So if you have a scalable blockchain platform, you won't have those kind of issues. And you can have, your gas fee will be low, so it will be very easier for people to actually get involved with your blockchain. So let me quickly give you a very, one application which is pretty interesting, and that can only be handled if you have a blockchain platform that's scalable. And that application is digital advertising. So if you're familiar with this space of digital advertising, it's a very big economy. You have big players like Google, Facebook, which are involved in this space, and it has $1 billion market economy. But it has its own issues. You have, on one hand, you have advertisers who want to advertise their product, and on the other hand, you have publishers who actually publicize the ads. But what actually happens in this ecosystem is that you have all kinds of players, all kinds of middlemen that sit in between an advertiser and a publisher, and they all take a cut out of what is supposed to go to a publisher. Then you have issues like malicious ads, or ads that have no relevance to users. So sometimes you go to certain websites and you're shown some weird ads that doesn't concern you at all. And what happens in the end is that you would use ad blockers, and you'd block those ads. And when you use ad blockers, you're actually damaging the ad-based economy that supports a lot of internet applications and online services. So there are a bunch of other issues that you can think of around this digital advertising space. And it's not just us, but many people in the digital advertising space, they are looking into how to leverage blockchain and its transparency and auditability properties to build an application, or to build a supply chain for digital advertising. But the problem is that if you want to build such an application, or such a supply chain application on a blockchain platform that exists today, you won't actually be able to do it. Because let's say if you forget about latency for the time being, if you just focus on how many ads are actually delivered to users per day, Google alone, delivers around 1 billion ads per day. And if you look at, let's say, Ethereum, for instance, Ethereum processes around 1 million transactions per day. So even if, let's say, blockchain like Ethereum decides to process only ad-related transactions, even then, the blockchain network won't be able to process or handle such an application. So you certainly need a blockchain platform that is actually scalable to even to support such a very popular and a remarkable application that you can imagine. And this application is very interesting because it involves a lot of players. It involves big companies, let's say like advertisers like Adidas, for instance. It also involves big players such as BBC, New York Times, for instance, who actually publish your ads. And it also directly relates to you as well as a user because you are actually going to visit see those ads. So it's a very large ecosystem. And if someone is able to actually tap into that ecosystem, it would ensure that your blockchain can actually be adopted by different players in the market. So in short, we are trying to work on this as well. We are partnering with a company called Mindshare, which is a digital advertising agency. And the goal of this collaboration is to understand what are the problems that they actually face in real world and how can you actually solve them. And we'll work together to build an application that would actually take at least a part of that supply chain on blockchain to ensure that certain parts of the system can be made more transparent, or certain parts of the system can be made more auditable, so that you could remove certain middlemen that exist in the current scenario. Digital advertising is just one application. You could think of other applications that actually require very high throughput. For instance, imagine building an application like Uber on blockchain. You just can't build with existing platforms. You need a scalable blockchain platform. And we feel that any of those applications that you can think of, which requires moderately high or moderately large throughput, you won't actually be able to build those on platforms that exist today. And there are many other applications that you can think of. Even the simplest one, which is payments, where you just want to transfer money from one account to the other one. Even for this simple application, you need a scalable blockchain platform. So in short, scalability is very, very important. And we at Zilliqa are trying to solve this problem using this idea of sharding. We have a testnet which is live. So this testnet is in the state where you can interact with the testnet, so you can send transactions and see how quickly or how much throughput you can get from this network. You cannot join the network for now, but we will be opening this network very soon. So you'd actually be able to run a node in the network and be a part of the system. We are also building a smart contract platform that will be live in a few months' time. With that, thank you so much for your attention. I'll be happy to take a few questions now.
All right, questions for Zilliqa. Do you have any questions in the audience? Just raise your hand.
I have a question. Hi.
Perfect.
I'm a cryptocurrency engineer, and I studied blockchain technology at the Lund University in computer science. So you said that the problem with raising the block size in order to scale was the bandwidth requirements gets too high because there's so many transactions that needs to be propagated over the whole network. So with your solution, how do you shard the network without knowing the network state? So because you need to shard the entire network, any node that wants to participate in the sharding will have to know the full network state. And in order to do that, they also need the full set of transactions that has happened in the network. So how do you actually avoid the problem of having to propagate every transaction in Zilliqa? And
okay,
by the way, if you go to the Ethereum sharding frequently asked questions, the FAQ of Ethereum, you will see that they have also criticized your approach for not actually solving how you shard network state, but you only solve one part of the problem, which is sharding transactions processing. So how do you respond to that?
So we are not doing state sharding. we are not doing it's sharding. What we're trying to do is this network sharding and transaction sharding.
But that is the bandwidth requirement that you have
No,
to
so
solve.
what you can do is, what we're trying to do at Zilliqa as well, is that when you send a transaction, you send transaction in an asynchronous manner. So you don't have to wait for the network to send you the transaction to actually process the next transaction. So it's not the, let's say you don't, every single node will have to store the entire state of the system.
Yeah, so if every node has to store every transaction in the system,
Yes.
then how do you limit the bandwidth requirements in your system?
No, but you are not creating a huge block, right?
Yeah, but you're still propagating all the transactions. So if it's millions of transactions per second, then you will still have to broadcast 1,000,000 transactions per second.
Yes,
over
but
the
you
whole
could do
network.
that in a completely asynchronous manner.
So it doesn't matter if it's asynchronous, it's still a bandwidth limitation.
It's different, right? I mean, we can take this offline if you want to discuss.
Yeah, well, if you don't believe me, go to the Ethereum frequently asked questions. You can see that they criticize the Zilliqa sharding approach exactly for this reason. And I would really like to see a real answer to this question. So thank you.
Sure.
More questions to Zilliqa? Raise your hand.
Thank you. It was a very interesting talk. Why don't you choose to work together with Ethereum more to build sharding out there? And why did you choose to build your own project?
I'm sorry, I didn't catch your question.
So
Yeah.
why do you not choose to work with Ethereum and do sharding together with Ethereum?
Well, we would love to collaborate with any project that exists out there, including Ethereum. And if you have an opportunity to work with them, we would certainly work with them.
Sorry, yeah, just one more, sorry. Could you maybe explain a little bit what happens if one of the shards basically goes down to the rest of the system? How is it affected? Thank you.
So if you have just one shard in your system, then your system will go down. But what we'll have is you'll eventually have a lot of shards. And even if a shard goes down, you still have other shards that can process.
Sure, but in your example, for now, you have 6 shards, correct?
In our case, yes,
exactly.
yes, 6
So
shards, yeah.
with 6 shards, if one goes down, how does it affect the other 5? Do you lose
You
many
will only,
information?
so let's say so currently each shard is able to process around 400 transactions per second. So you'd lose that in terms of throughput.
Okay, thanks.
More questions?
Yes.
We have one in the front.
So I have a question regarding the new language, Zilliqa. So it's the language itself, it's Turing incomplete, right? And as far as I know, there are no really big programming languages out there that are Turing incomplete. So it will, I can be mistaken, but it might be one of the first programming languages that can be big, potentially, that is Turing incomplete. And if I understood it correctly, I have a master's degree in computer science, but I'm no expert about this in particular. But Zilliqa being Turing incomplete means that we cannot represent any other Turing complete program that was, or rather a program that was written in a Turing complete language. So it would be interesting to just get some quick reply regarding what kind of limitations we can expect from Zilliqa being Turing incomplete.
Sure. So Bitcoin scripting language is also Turing incomplete, right?
Okay.
So if in Zilliqa, what we have, the only missing bit in terms of Turing completeness is loops, is infinite loops. If you look at our paper that we have on Zilliqa, we actually have written a Kickstarter program in Zilliqa, which is very close to, let's say, your ERC20 ICO-like contract. So it's still very, very expressive. And the only, I mean, even if you look at, let's say, a Turing complete language as solidity, even if you write, let's say, an infinite loop in your contract, it will never run because of gas limit and block gas limit that you have. So Turing completeness is not that necessary in the sense that even if it's Turing complete, it won't actually be run in a Turing complete manner per se. So the language is very, very expressive in that sense. So I can say that you could write almost every single application that you actually see today in Zilliqa.
Okay, great. Thanks.
Thank you.
And just as a follow-up, so what is the reason why don't you have a Turing complete language? Is it because of spam? Is it a spam prevention?
Essentially, you want to. So the idea was not to make it Turing incomplete, directly. The idea was to structure the language in a way that you could eliminate certain bugs. For instance, reinferencing. So in reinference, in order to prevent reinferencing, you have this idea of putting the send instruction at the end of the function. So if you could impose that at the language level, you could actually make certain, you could guarantee that certain attacks won't happen. So that was the main idea, and then we felt that loops are, infinite loops are anyway not necessary. You don't need that anyway. So Turing incompleteness was not our focus. It just happened to be Turing incomplete at the end of the day.
And what is your opinion on Cardano and their functional programming approach to their programming languages?
So it's very, very close, I would say, to some extent. So their programming language is based on lambda calculus. Our programming language is based on what's called input-output automata. So essentially, you have automata and you talk. Each automata talks to another automata. So it's very close in terms of in the fact that they are very close to functional programming to some extent. But again, we are taking different approaches.
And I personally think that functional programming will play a bigger role going forward because of formal verification and being able to prove what your smart contract does. And this is something we talked about before. You see so many hacks. Smart contracts being written in a non-secure way. So being able to prove mathematically exactly what your program does is very important.
Sure. Just to let you know that we are going to do a live demo on 23rd of January this year. 23rd of May this year in Singapore, where we are going to show a functional prototype of Zilla, where we'll show that how you can actually write a contract, a crowdfunding contract in Zilla, and what are the properties that you can prove in Coq, and what happens if you introduce bugs into that contract, and how the proof actually gets affected.
Yeah. Very interesting. So thank you so very much, Amrit. You also get a present for us, Horror Wallet, so you can store all your crypto. Thank you so much for a very good talk, and a big round of applause for Amrit from Zilliqa.